So welcome to the next topic, methods of purification and separation. So these are the learning objectives for the unit. We're going to understand how to classify a substance as an element, compound, or mixture, demonstrate knowledge and understanding of something known as paper chromatography, interpret simple chromatograms including something known as an RF value, identify substances and assess their purity from melting point and boiling point information, which we touched on in the last unit in fact, and describe and explain methods of purification by the following methods: simple distillation, filtration, crystallization, and fractional distillation. So two different forms of distillation there. So first things first, what's an element, a compound, or a mixture? Okay, so what I want you to do is pause the video now, go away and try and define an element, a compound, and a mixture, and give an example of each of these different things. Okay, so these are some definitions that I have. Yours might be slightly different, and I might have also given different examples. However, a chemical element, which we'll usually just call an element, is a pure chemical substance consisting of a single type of atom. So the example I'm going to give is gold, which means that the element of gold only consists of atoms of gold. A compound is a substance formed when two or more chemical elements are chemically bonded together. So the example I'm going to give is water, where you have hydrogen atoms and oxygen atoms chemically bonded together. And a mixture is a material system made up of two or more different substances which are mixed but are not combined chemically. Okay, so for example, a mixture of hydrogen and oxygen means that they're not actually chemically bonded, they're just together in the same container, but they're not bonded to form water. Okay, so a mixture would be a mixture of hydrogen and oxygen, say in a balloon. And there's a visual representation of that. Okay, so the atoms are represented by the single purple and green spheres. Molecules are represented by two or more spheres joined together. Okay, so these are the elements here. And notice that even though these guys are molecules, they're still only elements because they're only one type of atom. You have mixtures, and notice that in mixtures, they are not chemically bonded together. So that means that they are mixtures. And molecules of compounds are represented where they're actually chemically bonded. Okay, these different atoms are chemically bonded together, so they are compounds.
This unit will help you understand elements, compounds and mixtures and their differences. And the last section will look at the separation techniques you need to know for your test. So we'll start with elements. All materials, everything around us, are made up of chemicals and can be classified as either living or non-living, ranging from complex structures like ourselves and this plant to what look like simpler things like paper and plastic. Everything is made up of chemicals, and for your test you need to know about different types of chemicals and some of their properties.
Chemicals aren't just things you find in labs. Everything around you is made up of chemicals. This cake is made from all these ingredients.
But what are the ingredients made out of? They're all made out of chemicals called elements. Elements are the building blocks of everything around us.
This lot certainly don't look very tasty. In fact, some of these elements are toxic and dangerous.
So, what's special about elements? They're pure substances that cannot be split up into simpler substances. All elements are made up of tiny particles called atoms, and each element is only made up of one type of atom. Elements can be represented by a symbol, and you've probably heard of some of the most common ones. N for nitrogen, O for oxygen, Fe for iron, Hg for mercury, S for sulfur, Cu for copper, and C for carbon. At room temperature, elements can be solid, liquid or gas, so that the elements nitrogen and oxygen, gases, look very different from the elements copper and carbon, solids. So you need to know that elements are pure substances and are only ever made up of one type of particle, called atoms. We see very few pure elements in everyday life. Here's mercury in a thermometer, silver and gold jewellery, and helium gas is used to fill balloons. Elements are rarely seen because they're so often combined in chemical reactions to form compounds. Watch what happens when we combine the two elements sodium and chlorine gas.
Elements are made up of tiny particles, too small to see with the naked eye. Particles of one element are all the same. Imagine these are particles of the element sodium. Chlorine particles are very different from sodium particles. But when particles of different elements get together, two things can happen. They can be mixed together, but they keep their own characteristics and are easily separated. Or they can join together chemically. They're much harder to separate now. The chemical combination is called a compound.
So a compound is a substance where two or more elements have joined together chemically, and the combinations of elements within these compounds are always in fixed proportions. Mixtures are made up of particles of substances which have not been joined together in a chemical reaction. Here is a mixture of sulfur and iron. They have not reacted chemically and can be separated easily. The iron is magnetic and can be easily collected up with a magnet. My cup of tea is obviously a mixture. It has several ingredients. But how about the ingredients themselves? Here's a question for you. Are each of these, milk, sugar and water in my tea, mixtures or compounds? Why not stop the tape and have a think? So, which of these three examples are mixtures and which are compounds? The answer is only the sugar is a compound. It only contains one substance. Remember, in a compound, the particles are combined chemically and they are all the same. Milk is a mixture of fat and water, minerals and vitamins, and ordinary tap water, well, it looks pure enough, but it is in fact a mixture. There are other things in it. In this next clip, Femi goes under the Derbyshire Hills and takes a closer look at the local water supply there.
Stalactites are formed by dripping water over thousands of years. The drip of water dries up and leaves behind tiny crystals of calcium carbonate.
Calcium carbonate, a compound. Ah, so already we know that the local water must contain calcium.
And the band of orange on the wall indicates that there's iron in the water that's passed over this area.
So that could be in the water too?
Correct.
Alan showed me examples of other substances like manganese left behind by the water. It looks like there could be much more than just the elements hydrogen and oxygen in the local water.
This is the lab where the local water is tested, and Karen here does the testing. Can you help me out here? I'm a little bit confused. The locals call this water pure, the leaflets call this water pure, even the bottle claims it's pure, and yet it looks likely that it does actually contain calcium, iron and manganese.
Yes, you're right to be confused. That's because the everyday use of the word pure is somewhat very different to the scientific use of the word pure. This sample of water is actually a mixture of water and all of those minerals that you mentioned earlier. Pure water contains entirely the elements hydrogen and oxygen.
So where can I find pure water then? Scientifically pure, I mean.
Well, if we take this sample of water for starters, I'll show you what we can do.
Karen heats up the mineral water till it starts to boil. The minerals in the water can't boil off, but the pure water can. The pure water vapour passes up through this tube. The tube is kept very cool, so the water vapour condenses and water trickles out the end, scientifically pure water. But when all the water's boiled away, what's left in the flask? You can clearly see traces of minerals left behind on the side of the flask.
So scientifically, the mineral water is no more pure than my fizzy drinks.
Indeed, they're mixtures too.
But that is pure water.
Yes, this is pure water. It's actually tasteless, and it's the minerals that give the water its unique taste.
I think I'll stick to the natural, but not scientifically pure, Buxton water. Cheers.
So when referring to the word pure in chemistry, pure means a substance which contains only one type of particle. Mixtures are a combination of substances that are not chemically combined and can be separated. So ordinary water that we drink and use for everyday purposes is in fact a mixture of water and minerals that are dissolved in it. We can get pure water with nothing else in it by distillation, but that's in the next section that we're going to look at. In chemistry, mixtures often need to be separated, and in the next section we're going to look at the separation techniques. There are 5 different separation techniques you need to know for your test, and also when you would need to use each one. In this next clip, several different separation techniques are used to separate salt out from rock salt. Try writing down all the ones you see.
It's the only rock salt mine in the UK, and it's enormous. Hi, George. Yeah, I've collected my rock salt sample for analysis, so what do I need to do?
Well done, Trish. And I put the rock salt nicely on the weighing paper.
Lovely jubbly. Take 100 grams of fresh crushed rock salt. Add water and mix well for 2.5 hours. The salt dissolves, but of course the clay does not. Pour the mixture through a filter. The clear salt solution passes straight through into the flask. But the brown clay particles are too big to get through the filter paper. Heat the salt solution. The water evaporates, but the salt is left behind. By subtracting the weight of an identical empty beaker from the weight of my salty one, I can calculate I have 94.8 grams of salt.
So, what separation techniques did you come up with? You should have come up with 2 separation processes. The clay and salt were first separated by filtration, and secondly, evaporation. The salt solution was heated, the water turned to water vapour, and the solid salt left behind. But if you had a salt solution, and this time you wanted to keep the liquid and not the solid, the salt, then the separation process needed is different.
You may wish to separate a solution of salt water and keep the water. In this case, the solution is heated in the same way, but the water vapour, or steam, is trapped and channeled into another container where it cools and returns to liquid. Separating a solution in this way is called distillation.
So filtration is used to separate a solid from a liquid. Evaporation is used when you want to separate a soluble solid from a liquid when collecting the solid. Distillation is used when you want to separate a soluble solid from a liquid, but this time you want to keep the liquid. When a mixture of liquids needs to be separated out, for example this crude oil, a process called fractional distillation is used. The different liquids have different boiling points, and as the temperature of the crude oil rises, each liquid in turn reaches its boiling point, vaporizes, and then condenses back again into the liquid. Fractional distillation is used when a mixture of liquids with different boiling points needs to be separated out and collected in large quantities, like the example we just saw, crude oil. But what happens if our liquid comes in very small amounts? Ink is made up of several different pigments, and to separate these colours out, an entirely different process is needed.
Ink is a mixture of coloured dyes dissolved in water. The mixture, or solution, can be separated to show which colours it contains. It's then possible to find out what kind of ink was used. The writing on this piece of card looks as though it was drawn with one kind of black ink. We can test this by taking a sample of the ink used for each letter and placing it on a special paper that acts like blotting paper. The dish contains a small amount of chemical in the form of a liquid that will dissolve the ink. By leaving the paper to stand in the dish, the liquid will gradually soak into it and move upwards. The liquid causes the dyes in the ink to move with it up the paper. As some dyes move faster than others, they'll start to separate from each other, showing the different colours contained in the ink. The patterns that look the same were written in the same ink, but the different patterns in the other samples show that more than one ink was used on the card. Separating ink dyes in this way is called chromatography.
So fractional distillation is used to separate a mixture of two or more liquids that have different boiling points. Chromatography is used to separate very small amounts of two or more coloured dyes. That brings us to the end of this section. Don't forget, there is more information in the series book and on our website.
Okay, so now we've looked at compounds, elements, and mixtures. Let's look at the idea of purity and impurity. Okay, so a pure substance is one which has no other substances mixed in it. So pure gold only has these gold atoms. There's no other atoms inside that gold. Okay, and an unwanted substance, so if you had a little bit of, say, copper in your gold, that would be known as an impurity. And chemists check purity by comparing melting and boiling points. Okay, so pure water, for example, will boil at exactly 100 degrees Celsius, and pure water will also melt at 0 degrees Celsius. So if the melting point or the boiling point is different, then it means that the water is probably not pure. Okay, so when a reaction occurs, you need to find out, you want to end up with a mixture, and you want to purify that mixture, because inside that reaction it's going to have reactants and other side products that you may not want. Okay, so this requires techniques to separate mixtures of particles. Okay, and here's a whole range that we're going to look at. So at the end of a reaction, you might have a mixture, which could be an insoluble solid and liquid, so you would separate by filtration. If it's a solution of solid and a liquid, if you want to obtain the liquid, you'd use something called distillation, which we're going to learn about soon. If it's going to be a solid you want to obtain, then you want to separate by crystallization. If you have two liquids that dissolve in themselves, okay, which are soluble in each other, which is known as the word miscible, then you would use fractional distillation. And if you have a solution containing a mixture of small amounts of solids, you would separate by chromatography. Okay, so that's the first one we're going to look at is filtration. Okay, so suppose you had a mixture of insoluble solid and a liquid. So a solid that does not dissolve in the liquid, say concrete in water. Okay, how would you separate it? Okay, well, you'd use filtration. So in filtration, a suspension of an insoluble solid, so a suspension is these fine particles of the solid that doesn't dissolve in the liquid, all in the liquid, is passed through a filter, which you see on the diagram here, and the solid can't get through because it can't get through the holes in the filter paper, and it's stuck on the filter paper, and that's called the residue. And the liquid that passes through into the beaker in this example here is known as the filtrate. So that was simple filtration. We also have something known as crystallization. Okay, so in crystallization, if the solid is soluble, then the solution can be separated by crystallization. So what we're doing there is that the solution is heated with the Bunsen burner here until the liquid starts to evaporate off, okay, the solvent as it were, and as the solution cools, the crystals form as the solution is more concentrated, and the crystals are then filtered off with the filter paper, just like in the previous slide. Then we also have distillation, and there's two types of distillation: simple distillation and fractional distillation. We'll look at simple distillation first. So distillation allows you to separate a liquid from a solution. The solution is heated, and as the liquid evaporates, okay, so it's going to be heated over here. As it evaporates, obviously vapors are going to form. The soluble salt is left behind, and the vapor rises and gets put through something called a condenser, which cools down the vapor into a liquid again. It condenses it, and the vapor forms back into form of a liquid, and this is known as the distillate, which you can collect in a conical flask. That's simple distillation. We also
Crude
have
oil is a thick,
distillation.
dark brown liquid found deep in the Earth's
And if you have
crust.
two liquids you wish to separate, you can use
It's a
different
mixture
boiling
of different
points to separate
hydrocarbons,
them.
molecules
And this is
made
done
of
by
hydrogen
first
and
boiling the
carbon.
mixture of solutions and the
Some molecules in the mixture are very small, just a few atoms joined together. Others are far more complex, with many atoms forming long-chain molecules.
So you can collect that one first and then
But as a mixture, it's useless. The different hydrocarbons need separating.
them in fractions. And this is how
The technique
we can,
used is
distill,
distillation.
For example, alcohol.
This simple apparatus is set up in a fume cupboard. Mineral wool stops the mixture spitting when it's heated. Crude oil is dropped into the bottom of the tube. A collecting bottle is put in place. And a thermometer level with the sidearm monitors temperature. The final step is to gently heat the mixture by immersing the tube in a hot water bath. The hydrocarbons with lower boiling points begin to vaporize immediately. They're flammable, so it's safer not to heat with a naked flame. As the vapour rises, it enters the sidearm, where it cools and condenses. This happens at about 40 Celsius. The hydrocarbons which boil at this temperature drip down the sidearm and form our first fraction. It's a colourless liquid. The temperature stays at around 40 until all the hydrocarbons with this boiling point have vaporised. The hydrocarbons left behind aren't hot enough to vaporise. Their boiling points must be higher. Once the first fraction has been collected, it's safe to start heating with a Bunsen. As the temperature rises, other hydrocarbons begin to boil. A new fraction is collected at about 60 Celsius. It's slightly yellow in colour. And so the process continues. By carefully heating the oil and collecting the liquids which condense at a number of different temperatures, the many different hydrocarbons in crude oil can be separated. This is known as fractional distillation. On a larger scale, a fractionating column is used. The oil is heated with an electric heater for safety. The vapour is condensed by a Liebig condenser and is collected in a conical flask. Hot vapour rises up the fractionating column. It's a long way to go, and the further from the heat source, the cooler it gets. Most of the vapour condenses on the glass spiral inside the column and drips back into the mixture. Only the hydrocarbons, which are still vapours at the very top of the column, enter the sidearm and condense to liquid. Industry uses the same process, but on a mammoth scale, in huge fractional distillation columns. The hot oil enters near the bottom, at a temperature of 330 degrees Celsius. The column becomes cooler towards the top. Fractions which remain as vapour at 85 degrees Celsius go straight to the top and are piped away. Different hydrocarbons condense at different temperatures, running off at various levels. Those with lower boiling points are collected at the top. Those with higher boiling points run off nearer the bottom. The longer the molecules, the higher the boiling point. Industrial distillation separates crude oil into useful fractions, each containing molecules of a similar size.
And finally, we have paper chromatography. So in this, you have concentrated solutions of solutes are made in a solvent, so they have to be dissolvable in the solvent. Dots for each of these solutions is then placed evenly on the bottom of a matrix. So usually for paper chromatography, that matrix is paper, so the name, and the matrix is then placed in a container with a small amount of solvent in it and closed. The solvent rises until the top of the matrix is removed. The solvent rises into the top, and then this matrix is removed. Okay, so it gets up to this point here, and then the paper is removed, taken out of the container. Okay, and the impurities can be separated based on how they bond with the matrix, and every compound has a particular retardation factor, an RF value, which you see with these certain dots. Okay, that's known as an RF value, a retardation value. So retardation is how much it is stopped by the matrix, and it's based on what the solvent is and also what the matrix is. Okay, in paper chromatography, that's obviously going to be paper. And the RF value, this one here, is going to be the distance the compound has traveled. Okay, so for example, this guy here has moved 4 centimeters, and the distance, total distance, the solvent has traveled. So his RF value will be 4 divided by 10, which equals 0.4 for that particular blue compound. And that's known as a retardation factor, or an RF value, and it gives you an indication of what impurities and compounds are in your solution.